We're going to do calculations with heat and humidity. So first of all, how do you measure humidity? You can cool the air and weigh the moisture that comes out of it. Okay, you could chemically absorb the moisture, so compounds that will absorb it, and then look at the change in weight of those chemically absorbent materials. Okay, or you could correlate some of their properties, such as thermal conductivity, if that changes with the water content in the air. You could use infrared spectra or a Sling psychrometer. Okay, so for example, thermal conductivity, let's say you want to have a device that would measure this. You know that thermal conductivity of air with changing temperature, if you have no water, okay, it's fairly linear, but as you have more water, then it's going to change, okay, with that humidity. So you can look at you can measure thermal conductivity, for example, and then infer the humidity. Okay, so that's how you measure it. So let's just talk about the wet bulb temperature first of all. Okay, so thermometer has a wet cloth around the bulb. The air blows past the cloth, and as the water evaporates, the bulb is cooled. So it's like kind of like when you get out of a swimming pool, you get cold if it's not very humid outside. Okay, so the difference between the dry and the wet bulb temperatures is related to the relative humidity. And so no water evaporates at 100% relative humidity, so the dry bulb temperature equals the wet bulb temperature. And the biggest delta temperature between those two is with the driest air. Okay, so let's just look at a Sling psychrometer. So you have two thermometers. One is dry and one is kept in a wet cloth. And then you twirl the wet thermometer, high velocity through the air, and then you're going to measure the dry bulb and the wet bulb temperature. Okay, so that's one way to do it. There's some other psychrometers as well. Okay, so let's just go into some air-water systems. So, very common in engineering. You have refrigeration systems. You have air inlets to processing equipment, for example, and you want to be able to know how much air is there and maybe the enthalpy or some other properties of that air. Okay, so there's a chart that's developed for ease of use, and there's lots of data on that chart. Okay, so we're going to cover that chart and do a couple example problems today, but it's based, one thing to remember, it's based on dry air balance. Okay, so with no water in there, that's going to be in the denominator. So for example, we previously covered an example like this where you have humid air, you have a cooler, and you have to find out what temperature T1 is in order to get 70 degrees Fahrenheit and 30% relative humidity after you heat it. Okay, so this is going to be 100% relative humidity here, and then what you can do is find the water content here and find out what temperature that becomes 100% relative humidity. So we've done that in the past, but now we're going to go on to this psychrometric chart. Okay, so there's a lot going on this chart, and just a couple things to note are that this is an air-water system at 1 atmosphere. Okay, so if it's different than 1 atmosphere, it's going to change. Okay, and then the other thing is there's your dry bulb temperature on the x-axis. Okay, so there's, for example, about 20 degrees Celsius. And as we go up, this is, so anywhere along this line is going to be dry bulb temperature of 20 degrees. Okay, and then here on the y-axis is your moisture content, and that is kilograms of water per kilogram of dry air. Okay, so this is on a dry air basis, and the denominator is dry air, but it's how much water you have divided by the mass of the air. Okay, and so you can see these numbers are very small. So 0.03 kilograms of water per kilogram of air, for example, would be right here. Okay, so and this would be, for example, 0.011. And so if we had a dry bulb temperature, there, and also this water content in the air, then we would come over here at the intersection of these two, and that's where we would have our point. Okay, so for this chart, the reference state is for liquid. It's at 0 degrees Celsius and 1 atmosphere, and the dry air is also at 0 degrees Celsius and 1 atmosphere. Okay, but this is for this chart only. It's going to be different for other charts. Okay, so just keep that in mind, because enthalpy is, we often compute deltas, and so if you mix and match enthalpies from different charts, it can often lead to great errors. Okay, so let's go and trace the line of 40% relative humidity. Okay, so here is relative humidity. There's 50%, 60%. Okay, and then there is 40%. Okay, so anywhere along this line is going to be 40% relative humidity. Okay, and now let's trace the line of 22 degrees wet bulb temperature. Okay, so that's going to be wet bulb temperature right there, and there is 20. Okay, so this was 20 right here, and this is going to be the line right here corresponding to 22 degrees wet bulb temperature. Okay, so let's trace the line of humid volume of 0.85 meters cubed per kilogram dry air. Okay, so so here's our humid volume. That's meters cubed per kilogram dry air. Okay, and then and just remember that's meters cubed of air plus the water vapor. Okay, divided by the kilograms of dry air. Okay, and so there is the humid volume. Here's 0.9, for example. Here's 0.8, 0.75. Okay, so let's trace the line of saturated enthalpy of 65 kilojoules per kilogram dry air. So it's right here, and it's just going to go straight down. Okay, here. Okay, so that's 65 kilojoules per kilogram dry air. Okay, so this is the enthalpy of the air plus moisture divided by the mass of dry air. So remember, it's on a dry air basis. Okay, so what if I want an enthalpy that is not saturated? Okay, so for example, at 50% relative humidity. So there's this deviation on the chart. And so what you do is you take the saturated plus this deviation. Okay, so let's go to trace the line of enthalpy deviation of 0.4 kilojoules per kilogram dry air. Okay, so this is your enthalpy deviation right here. Okay, and there is negative 0.4 right there. So if you have different relative humidities, then that's going to change your enthalpy. And so that's how much you have to add to it. So it's going to be actually subtracting 0.4 from that number if you have this, for negative 0.4, this is the line. Okay, so let's go on. When working with these charts, what is the enthalpy of liquid water? Okay, so if we are extracting, for example, some liquid water at a different temperature than the reference, so the reference is 0 degrees or 32 degrees, 0 degrees Celsius or 32 degrees Fahrenheit, then we just go ahead and integrate. Okay, so this is going to be reported, this is our 0 value right here, and then what we have to do is just integrate the heat capacity of the water. Now liquids, for example, liquid water, it's going to be about constant. Okay, so this is going to be pretty close to a constant, and we typically use values of like 1 BTU per pound mass degree Fahrenheit or 4.184 joules per gram degree Celsius or Kelvin. Okay, so let's go over an example then. If we have liquid water at 45 degrees Fahrenheit and 1 atmosphere, then we would use the heat capacity. Let's go ahead and use this one right here, and then we just multiply by the delta Fahrenheit. Okay, so that gives us 13 BTUs per pound mass. Okay, so let's go over an assignment now. Okay, so this one I'm going to go ahead and go over here. Let me make this just a little bit bigger. We'll read over the assignment and then look at some of these charts. Okay, so the psychometric chart for air and moisture, water at 1 atmosphere total pressure is shown on the next page. So please complete the following. Air at 1 atmosphere and 28 degrees Celsius, 70% relative humidity, and then we'll label this as point A. Okay, so let's just go over here to the psychometric charts. You'll see here that this psychometric chart is, this one's degrees Celsius, whereas the one that's below it is just going to be in degrees Fahrenheit. So same one, just different units. So let's just look at this one because our problem statement was given in degrees Celsius. So it's air at 1 atmosphere and 28 degrees Celsius and 70% relative humidity. Okay, so here's our 70% relative humidity line right here. Okay, so I'm just going to draw that. Okay, and then we had 28 degrees Celsius. Okay, so there's 25, there's 30, and there's 28. Okay, so I'm going to come up. Okay, so that's going to be my, okay, so this is going to be my dry bulb temperature at 28. Okay, so absolute humidity. So what we're going to do is we're just going to go ahead and come over to the right. Okay, and there's my absolute humidity. That's going to be the first one. And that's 0.0165. And remember, that's going to be the pounds of, so in this case, let's see, so this is 28 degrees Celsius. Okay, so that's going to be kilograms per kilograms dry air, or it's also going to be pound mass per pound dry air. Okay, so it's the same thing, pound or kilogram, just a ratio of the two. Okay, so let's look at our wet bulb temperature. Okay, so wet bulb temperature, that is going to be, okay, so follow the enthalpy line up. Okay, so that's going to be about 23.6 degrees Celsius. Okay, so let's look at our dew point temperature. Okay, and that one, if I trace it all the way over here, that's going to be about 21.8 degrees Celsius. Okay, let's look at our saturated enthalpy. Our saturated enthalpy, again, we're coming right up here. It's about right there. That's about 71 kilojoules per kilogram dry air. Okay, let's look at our specific enthalpy. Okay, that was saturated enthalpy. Now we're going to look at our specific enthalpy. And so if we want to get that, we have to subtract, this deviation right here. So that was enthalpy at saturation here, but if we want to get the specific enthalpy, we also have to add, actually add this, but it's a negative number. So we'll take away about 0.2. Okay, so that's going to be 70.8, and that will be kilojoules per kilogram dry air. Okay, let's look at the humid volume as well. Okay, so here's 0.9, there's 0.85. Okay, so it's about in the middle, 0.875 foot cubed per pound mass dry air. Okay, so we use the psychometric chart to come up with some of these values. Now that was 28 degrees Celsius. Now in this case we're given degrees Fahrenheit. Okay, and then also a wet bulb temperature of 70 degrees Fahrenheit. Okay, so let's go look for this and then label it. Now we're going to go down here. Okay, so 80 degrees Fahrenheit, but 70 degrees wet bulb. Okay, so there's 80 degrees Fahrenheit, but 70 degrees on the wet bulb. Okay, so I'm just going to come up here on the 80 and then down here on the wet bulb. Okay, so there's my point B. Okay, so let's just go and do some more calculations. So absolute humidity. Absolute humidity, let's just trace this one straight over. Okay, so I'm going to say that's going to be about 0.03136, okay, pound of H2O per pound mass dry air. Okay, so that was my first one. Okay, so let's go ahead and compute some of the other ones as well. So we want to get the relative. The next one is going to be the relative humidity. So let's just find out what line this is on right here. This is 60, about 60, just a little bit over. Okay, about 60.5% relative humidity. Okay, let's get the dew point temperature. Okay, so that's going to be, just trace this straight over, and that's about 65 degrees Fahrenheit. Okay, we'll get the saturated enthalpy as well. Let's come up here. That's going to be about 34. That's 34, and that's BTU per pound mass dry air. Okay, now specific enthalpy. We want that one as well. So we've got to subtract this amount. Okay, follow these curves up. And okay, so this one right here. Okay, and let's see, this is negative 0.8, negative 0.6. Okay. So yeah, that's okay, so that's about 0.6 or so, it looks like. Okay, so I think I'm reading that wrong. Oh, 0.0. It looks like something didn't quite turn out here on the chart. Okay, I think these things are supposed to continue up, but I'm not seeing that. They just look like they kind of terminate right there. So let's see, I think there's something a little bit wrong with this chart, but it's going to be right in this region right here where those are going to intersect. We're going to add this in, but it's a negative number. So we're going to take our 34 and then subtract about 0.08 or something like that, wherever this would intersect if we could see the lines. Okay, so so I'm just going to write that here. Okay, so it's going to be about 34 minus 0.08, and that's going to be BTUs per pound mass dry air. Okay, let's go back and get the humid volume as well. Okay, so that is right here. There's the humid volume. Okay, and so this is going to be about right here. Okay, so that's going to, if we just interpolate between those two, we'll just say that's about 13.85. Okay, and that's going to be foot cubed per pound mass dry air. Okay, so we've got these 2 points. We did this one in degrees Celsius, this one was Fahrenheit, AES, this one was SI, SI units, AES. Okay, so let's do just one more here. So we have air is at 90 degrees Fahrenheit and 80% relative humidity, and it's coming in at 100 foot cube per minute, and it's cooled to 60 degrees Fahrenheit and 20% relative humidity. So we'll assume the liquid water leaves at 60 degrees Fahrenheit as well. So we'll find, first of all, the mass flow rate of condensed water. Okay, and then we'll find the cooling requirement in tons of cooling. So that's how much a ton of cooling is, how that is the cooling that's required to make a ton of ice per day. And so that's equal to 12,000 BTUs per hour. Okay, so so we're just going to go through and just fill in this table first of all. Okay, so to get this is I'm just going to call this point C. The other ones were A and B, and I'll call this one D. Okay, so let's just go ahead and go with what's coming in. So that's the air at 90 degrees Fahrenheit and 80% relative humidity. Okay, so I'm going to come over here to this chart. Let me just go ahead and erase some of these lines that I had drawn. Okay, so we want to do first of all 90 degrees Fahrenheit and 80% relative humidity. Okay, so there's my 90 degrees, and then let me get 80% relative humidity, and let's just see where those two are going to intersect. So it's going to be right up at the top. I'm going to kind of try to draw a straight line right up here. Okay, so there's the 90 at the top as well. And then 80% humidity, so it's right here. That's my point C. Okay, and then my next point, which is going to be point D, is the air coming out. So it's going to be cooled to 60 degrees Fahrenheit and 20% relative humidity. So let's just go find that. I've got my 60 and then my 20. Okay, so let's see, 60 is about right here, and 20 is right there, so that's going to be point D. Okay, so that tells us everything we need to know about those two. Now we can do the change between those two and try to get the mass flow rate of the condensed water coming out. Okay, so the mass of, let's go ahead and just do the mass of dry air. So first of all, we have 100 foot cubed per minute. Okay, and then we also know that the humid volume, okay, is going to be a foot cubed per pound mass dry air. Okay, so we can use that information to get this first one, which is the mass flow rate of just dry air. Okay, so that's going to be coming in. Let me get the humid volume here. So that's 14.5, there's 14.0. So it's going to be about 14.4. So I have, that's 100 foot cubed per minute. Okay, and then I'm going to multiply that by 1 over 14.4 foot cubed per pound mass dry air. Okay, and that's going to equal 6.94 pound mass dry air per minute. Okay, so there's how much dry air I got. I looked at the humid volume and was able to compute that from the 100 foot cube per minute. Okay, so let's get the water that's coming in as well. Okay, so this is, if I draw it over here, I get my pounds of moisture per pound of dry air. So this is my pounds mass of dry air per minute. So I just need to multiply by that fraction. Okay, so 6.94, and that's going to be pound mass dry air per minute, and then multiply that by 0.025, and that's going to be pound mass of water per pound mass dry air. Okay, so that gives me how much water is coming in, 0.1736 pound mass water per minute. And that's what's coming in. Okay, so we have a lot more dry air coming in. Okay, the N2 and the O2, and that's how much water is coming in is about 0.17. So now we want to compute, the water vapor that's leaving. Okay, so we're going to do. This is going to be 6.94 pound mass dry air per minute. Okay, so we know that that is not going to be condensed or consumed. And then let's just go over here and get, it's going to be about right here in terms of the pound mass of water per pound mass of dry air. Okay, so I'm just going to multiply it by that fraction, 0.0022, and that's pound mass of water per pound mass dry air. Okay, and that gives me a total of 0.153, and that's going to be pound mass of water, and that's going to be leaving, okay, per minute. Okay, so that's how much is leaving in vapor form. Okay, so the difference between these two right here, that's how much is going to be condensed. So that's the amount of liquid that's coming out. And actually, I forgot a 0 right here. Okay, so that's so this is very little coming out in the vapor. So most of that is going to be coming out in the liquid. Okay, and that's going to be 0.1583 pound mass of water per minute. Okay, so that's how much liquid is going to be coming out. So let's look at how much Q, how much heat transfer it took to do that. So what we can do now is just sum up all our inputs with the specific enthalpy, inputs and outputs, and then just took the difference between those two. So we'll go out minus summation of everything that's coming in. Okay, so what is leaving are the the liquid water, and then also the vapor. And so if we just go and get the enthalpies of those, so here is, for example, the enthalpy. Okay, and then we're going to subtract this deviation right there. Okay, this is actually going to be closer to the negative 0.04. Okay, and then up here as well. Okay, there's our enthalpy, and we're going to subtract this this small deviation. Okay, so I'm just going to do this calculation. We have everything that's going out, 0.1583 pound H2O liquid per minute. Okay, that's going to be the mass flow rate of this liquid water that's leaving. And we had let's see, so it's at 60 degrees, and we know that that's going to be 60 minus 32, okay, and then times 1 BTU per pound mass degree Fahrenheit, and so that's going to be 28 BTUs per pound mass for liquid. Okay, if we look up the other enthalpies here, we have here, we're going to have 48.5 minus 0.06, and so that's going to be 48.44, and then we had 16.8 minus 0.042, okay, and that's going to be equal to 16.76. I'll just put the volumes here. This was 13.15, and this is 14.4, and then 0.025 and 0.0022. Okay, so now we have all of our enthalpies of the in and the out plus the mass flow rates. So now I'm just going to do 28 BTU per pound mass liquid. Okay, so that's going to be coming out. And then let me do the other outlet stream. And that was 16.76. And BTUs per pound mass dry air. Okay, and then multiplied by the mass flow rate, 6.94 pound mass dry air per minute. Okay, so that gives me the enthalpy. This is all on a dry basis. Okay, and then I'm going to go ahead and subtract the input. Okay, dry air and 6.94 pound mass dry air per minute. Okay, so that is going to give me the heat. When I do this calculation, it's going to be negative 215 BTUs per minute. Okay, and that's going to be negative 12,925 BTUs per hour. Okay, so that's just over a ton of cooling. So that's going to be 1.08 tons of cooling, with 1 ton equal to 12,000. Okay, so that concludes this example. A lot of numbers here, but we were able to extract everything off of this chart. Okay, enthalpies, how much water per pound mass of dry air. Everything was on a pound mass of dry air basis, so there you can see that in the denominator in a couple of places. But we, first of all, in A and B, we just picked out points, and then in C we did a difference there. That allowed us to compute how much water was leaving the system, but also how much cooling we had to do to look at the change in enthalpy, okay, to get our Q value. Okay, so this example is done. Let me just go back and review that now. So here was 1 point. Okay, here's point A that we talked about. Okay, and there are all the values for point A. Here's point B. Okay, and all the associated values with those. Here's C and D. Okay, all of the values associated with those as well. And then there's how we found the liquid water out. And then we did the calculations to get our mass flow rates, our liquid out, and then our Q for the heat that had to be removed from the system. Okay, and that equaled 1.08 tons of cooling. Okay, so that's it for this presentation on psychrometric charts. We looked at heat and humidity, and particularly this air-water system, and just using these charts to do some of our calculations. We also talked, just briefly about how we measure the wet bulb and the dry bulb temperatures, and how that's useful. These air-water mixtures are very, very common in engineering applications. So that's why we have these charts and we do these types of calculations. Okay, thanks for watching.